How's the lockdown? Hello?
I said, they're fine.
You're fine.
I know it's nice.
It's nice.
I don't want to come back to school.
Oh, it's nice staying at home, ne?
Yes.
Okay. Right. Did you get the consolidation exercise that I sent through?
Yes.
Okay. Are you done with it, or are you still busy?
I'm done, sir.
You're done?
Yes.
Okay. All right.
Not sure of
Come again?
Not sure of others. Not sure of others.
Yeah, I see many people are not in yet. It's only about 3 people. I think it's only 3 people. Apiwe, Joshua, and the Vuo. Okay. Today, I don't know if there are any questions on the sections that we finished before. The ones that we finished before.
Which one,
especially
sir?
the consolidation one. Any questions there?
No.
No questions, no? Okay. So today I was planning for us to do magnetism, because the next topic is magnetism. Hello? Magnetism, ne?
Yes, sir.
Yes, sir.
Okay. All right. I'm just going to look at the basics of magnetism. Then in our next class, we're going to look at the Earth's magnetism, the true north, geographical north. We're going to be looking at that in our next lesson. So today, I just want us to look at magnetism for now. Then we'll continue from there in our next lesson. Okay, so let's look at magnetism. What do we have here? It's a continuation from what you've done in grade 7, grade 8 and 9. You did some static electricity. You did magnetic effect of current, electromagnets, you've done that. You've got some forces, different types of forces. I think you did this in grade 9, gravitational, magnetic, and electric fields. All right, then you in grade 10, we're going to be looking at magnetic field of permanent magnets, poles of permanent magnets, attraction, repulsion. We've got magnetic field lines. We've got the Earth's magnetic field. We look at the compass, how the compass works, right? In just aligning, indicating the direction using the magnetic field. Then in grade 11 and 12, you're going to be looking at electromagnetism, where you're going to look at generators and motors. You're going to look at Faraday's law in grade 11, right? Then electrodynamics, you do that in grade 12. Right, we move on. We've got some definitions there. You need to know the highlighted ones here. We've got a magnetic field. What is a magnetic field? It's a region in space where another magnet or ferromagnetic material experiences a force, all right? And that force is a non-contact force. We've got a contact force and a non-contact force. What is a contact force? It's a force that comes as a result of contact of objects. Like if for me to push something, I have to touch something and push it. So that's a contact force. A push and a pull, those are contact forces. When you look at magnetic force, an object can still experience magnetic force even though the objects are not in contact. So that's why it's called a non-contact force. Then we've got electric field. It's a region in space where an electric charge experiences an electric force, all right? Then the next one, we've got a magnet. What is a magnet? A magnet, it's an object with a pair of opposite poles called the north and the south poles, which experience magnetic force in a magnetic field, right? Next one, we've got a gravitational field. These are just definition in addition to that. A region in space where a mass experiences a gravitational force. Then we've got the law of attraction, and repulsion, which says like magnetic poles repel each other and opposite magnetic poles attract. So like poles repel and like poles attract. That's the law that we use for magnetic objects. Then we've got a compass, a device that uses a magnetic needle to show the direction of a magnetic field. Geographical North Pole, the northernmost point of the Earth's axis of rotation. So this is when as the Earth spins that direction that is up, we call it the North Pole. Then we've got what we call a magnetic North Pole of the Earth, the direction towards which the magnetic North Pole of a magnet points when it is free from any local magnetic influence. We'll talk about this later on. Then we've got solar winds, a stream of energetic particles ejected by the sun. These particles include electrons, protons, alpha particles, right? And atomic nuclei of carbon, nitrogen, neon, oxygen, and magnesium. Right, then we've got aurora borealis, which is the northern lights. This is the beautiful display of light in the northern hemisphere, which happens when the solar wind strikes the atoms in the Earth's atmosphere. We'll talk about this later on. Right, there's northern lights, aurora borealis, and we've got aurora australis, which is the one that happens in the southern hemisphere in Australia, for example. Yeah. All right, so we'll talk about that later on. All right, we'll move on to magnetism. So here, just as an introduction, magnetic fields are often confused with electric fields. All right, learners have difficulty distinguishing between positive and negative charge and north and south poles. So when we speak of north and south poles, that's we're talking about magnetism. So we have a magnetic field. When you talk of plus and minus, positive and negative, those are electrostatic or electric fields, or we normally use it in electrostatics where we look at stationary charges, right? Then some of the misconceptions that people have here: all metals are magnetic, right? Test for magnetic properties, e.g. iron, nickel. In South African coins, we've got copper, aluminum foil by bringing. So here, not all metals are magnetic, right? The magnetic one is nickel, cobalt, and iron. Those are the three materials that are magnetic. So you can try to test different metals and see if they are magnetic. Not all are magnetic. Unless they are made up of all those, they are part of the three, or there's some element of those three in that particular material, then they become magnetic. So some are not always magnetic. All right. If maybe you can do some research, there's also what you call diamagnetic materials. We also have what we call paramagnetic materials. There are different types of magnetism, right? We've got diamagnetic, we've got paramagnetic, we've got ferromagnetic. Ferro is the one that will be talking about here. The diamagnetic, the paramagnetic, that one, we're not going to be talking about that. But what I'm going to do, I'm going to send a video for you to distinguish between the three types. We've got ferro, dia, and paramagnetic. I'll send that. Even plastic is also magnetic, but it's not ferromagnetic. It becomes either diamagnetic or paramagnetic, depending with the lone pair of electrons in that particular element. Remember, when we are doing electron configuration, there are certain elements that have got two paired electrons, others have got unpaired electrons. It's going to be related to that. But it's not for our syllabus, just for your own interest here. Right, then a magnetic field exerts force on a stationary charge. Charge a perspex rod, hold it stationary, and bring it bring a floating compass up to it. The needle of the compass will not move when it is brought near the charged rod. Magnetic fields have no effect on stationary charges. So that's just a simple experiment for you to do to check if a magnetic field exerts force on a stationary charge. Then you've got magnets are formed by placing magnetic material in a magnetic field. Sometimes this statement may be true because you can magnetize some object if the magnetic material is made of hard iron. But in general, the ferromagnetic material loses its magnetism when it is taken out of a magnetic field, right? So ferromagnetic materials consist of clusters of atoms which act as tiny magnets. We call these domain. We're going to talk about this. This is some misconception before we start. Domains before magnetization are arranged. We'll talk about this later on, right? So in magnets, we've got what you call domains. These domains, they've got the north and the south, north and the south. So when you break a magnet, you always have small pieces, the north and the south. Those are what we call domains. We'll come back to that, I think, when we look at this. Whenever there is an electric field, there will be an induced magnetic field. The electric field around the stationary charge does not set up a magnetic field because the electric field remains constant. A changing electric field sets up a magnetic field. Therefore, when current passes through a conductor, there's a magnetic field associated with the current. This is how we make an electromagnet. So basically, what are we saying? We are saying when charges flow, then there is induced magnetism, right? That's how a motor works. Then if you've got a magnetism, then electricity will be generated or current will flow. That's how a generator works. We're going to be doing this in grade 12. Then magnetic fields can be blocked by surrounding the magnet with other materials, e.g. concrete, sand, aluminum, or an iron cage. The magnetic fields cannot be blocked easily. We know this because the Earth's magnetic field penetrates layers of Earth and you can still feel its effect. So this is not exactly true. It's a misconception that you can block. Maybe if the magnetic field is weak, you can block it. But like the Earth, on the underground, there is iron, and that iron is magnetic. That's what brings about the magnetism on the surface of the Earth. Even though they sand in between, we still have the magnetism coming through. Cutting a magnet in half will separate the north and the north pole, making a magnetic monopole. This is also a misconception. When you cut a magnet in half, it produces magnets. Each piece will still have its north and a south. So there are no monopoles. So you cannot cut a magnet and have only north and or only south. So that doesn't work. Right. Then next one, magnetic force and magnetic field are terms that can be used interchangeably. This is also a misconception here. We have a magnetic force and we have a magnetic field. A force is a push or a pull. A field is a region around a magnet in which another magnet or magnetic material experiences a magnetic force. So there's a difference between magnetic force and magnetic field. So please don't make that mistake that you interchange the two. Right, then we start. So for magnetism, it is an interaction that allows certain kinds of objects, which are called magnetic objects, to exert forces on each other without physically touching. Right, so that's magnetism. So you take a magnet, you have a paper clip or you have a needle, you bring it closer, it's going to be attracted. So there is that exertion of a force on another object. If it's far away, it will still move. So because it feels that non-contact force. Right, a magnetic object is surrounded by a magnetic field that gets weaker as one moves further away from the object. Right, so we're going to be drawing magnetic field lines. So they are closer at the poles, right, and they get weaker as you move away from the poles. A second object can feel a magnetic force from the first object because it feels the magnetic field of the first object. The further away the object, then the weaker the magnetic force. Right. Humans have known magnetism for many thousands of years. For example, there's something called lodestone. Is a magnetized form of iron, right? Iron oxide mineral called magnetite. It is the property of attracting iron objects, right? It has been there. I think it has been recorded somewhere in the 800 BC in Europe, and 2600 BCE in Asia. So magnetism, it was discovered quite a long time ago. Right, then we've got magnetic fields. All right, what is a magnetic field? There are different fields: electric field, magnetic field, gravitational field. So a magnetic field is a region in space where a magnet or object made of magnetic material will experience a non-contact magnetic force. That's a magnetic field, right? A moving charged particle is a magnetic field associated with it. One example of a charged particle that occurs in most matter is the electron, right? Electrons are in constant motion inside the material, orbiting. They are going around the nucleus in the orbits, like we have seen in the first term, in the atom, which may also be moving, rotating, or vibrating. So electrons inside any object are moving, and they've got magnetic fields associated with them. In most materials, these fields point in various directions. So the net magnetic field for an object, when you start, it's 0, because they point in different directions, so they subtract one another or they cancel one another. Right, in some materials like iron, right, are called ferromagnetic materials. There are regions called domains where electrons or electron magnetic fields line up with each other. All the atoms in each domain are grouped together so that the magnetic fields from the electrons point in the same way. So example here, you've got a needle here, right? So these are what we call domains. So there are many domains they are all pointing in different directions. So when you cut a magnet in pieces, those domains are still there. So you still have your north and your south because of the domains, right? So in each domain, the electron magnetic fields, the black arrows are pointing in the same direction, causing a net magnetic field in each domain. So when you add all of this, they end up having maybe a value of 0 because they're all in different directions, right? Okay, the poles of okay, let me just hold here. Any questions so far? Hello, are you with me? Hello? Guys, talk to me.
No questions so far.
No questions.
No
Okay.
questions, sir.
All right. We continue. We've got the
Yes,
poles
sir.
of magnets. Yes. We've got the poles of the permanent magnets. Because the domains in a permanent magnet all line up in a particular direction, the magnet has a pair of opposite poles, right? So a magnet will have a north and it will have a south pole, north pole and south pole, right? Even if the magnet is cut into any tiny pieces, each piece will still have both north and south pole. These magnetic poles always occur in pairs, so they always go in. There are no monopoles, like we say. There's always north and south. In nature, we never find a north magnetic pole or a south magnetic pole on its own. So we don't have monopoles. We only have dipoles, north and south, right? After breaking, so you're still going to have that part is still aligned. We still have a domain, so we still have north and south, north and south, north and south. Right, then we've got magnetic attraction and repulsion. So magnets, they do attract and they also repel. How do they, what's the golden rule here? Like poles attract, and unlike poles, sorry, that's this is mixed up here. Like poles repel and unlike poles attract. I'll post this, then I'll correct this. This is not right here. Like poles repel and unlike poles attract. So here, please don't follow this one. There's a mistake here. Right, this means that two north poles or two south poles will push away from each other while what is this? While north and south pole are going to be attracting. All right, so that's a mistake. I think it's Joshua typing here. Ne? Okay, right. Then we move on. Do you think the following magnets will repel or be attracted to each other? Here we've got the north and the north. So when they come together, north and north will repel because like poles repel and unlike poles attract. Then you move on to the next one. We are given two magnets with the north pole of one approaching the north pole of the other. That's for the top. At the bottom here, we've got poles which are different. So you've got south and north. When they come together, then they're going to attract. So unlike poles will attract. Then we move on to representing the magnetic fields. Representing the magnetic fields, you've got magnetic fields can be represented using magnetic field lines, starting at the North Pole and ending in the South Pole. So please, when you draw your magnetic field lines, they must always point from north to south. The direction there is always from north to south. All right. Okay. And the magnetic fields, they are three-dimensional, right? So they have a three-dimension. It's not only left and right, even top and bottom, sideways, there's still magnetic field. So it's a 3D representation of the magnetic field lines there. And another thing, when you're drawing magnetic field lines, please, they mustn't touch. The lines mustn't touch, right? Unfortunately, on this diagram here, I think here they are touching here, which is wrong. So for example, when I give you a question which says, draw the magnetic fields around a bar magnet, if you're gonna draw lines that are touching, like in this diagram here, then you lose 1 mark. The lines mustn't touch. They must always moving without touching. And also there's a mark for direction. So the direction must always be from north to south. If you say south to north, then it's incorrect. It must be from north to south. They must point towards the south. And from the north, they must be pointing away. That's the direction of the magnetic field lines. For example, here, if you have got iron filings, you take some small pieces of iron, you put them on a paper, then you put a magnet underneath the paper. Then you're gonna see the iron filings are gonna align like this, which is proof or just showing the magnetic field lines that result from that particular magnet. So they're gonna align themselves just like up here, showing the magnetic field lines. And you're gonna see they are crowded here at the top, which means the magnetic field is strongest where the magnetic field lines are closest. Just like up here, your magnetic field is strongest where the lines are concentrated here. That's where it is stronger. As you move away, it becomes weaker. The further you are from the magnet, the weaker the magnetic field. So your magnetic field lines, that's why also here they are spaced out, which means the magnetic field is weaker. All right, then we move on to the next one. When you're drawing the magnetic field for attraction or repulsion, this is what you're gonna get. You're gonna have your north, and you're gonna have your north there. And we know like poles, they repel. So your magnetic field lines are gonna leave a space here to show repulsion. All right, so this is how you represent the magnetic field lines for repulsion for 2 bar magnets, right? And there must be a space here, and the lines mustn't touch. And the direction, since it's north and north, your direction must point away it must be pointing away from the north. If it was south and south, then they all must be pointing towards the south. But still, the space must be there to show repulsion. There's still also a magnetic field around here, but here on this diagram only concentrated on this part here. But on the other side, there's still magnetic field lines here. You still have your magnetic field lines, but here just to show repulsion, this is what we have. Then when it is attraction, then you're gonna have lines as such. All right, so you're gonna have them running from north to south. And there's no space here, which shows attraction. So this is what you're gonna be having here. So this will be attraction. You see some different sources are gonna give you different diagrams, but the basic thing is what you have in between here. At the other side, they're gonna be different. Like when I send out the handout, I'm gonna try and put as many different diagrams for you to see how they represent the magnetic field lines. Clear? Right, so this is what I'd prepared for today. Tomorrow I'm going to try and prepare another one, which will be showing the geographic north, magnetic north, in the earth underneath, because we've got elements like iron, cobalt, and nickel. It means the earth also is a magnetic field. So we're going to be talking about the earth's magnetic field and highlighting the geographic north and the magnetic north. Then we look at the application, some of the proofs like the northern lights and so on and so on. Is that clear? Hello?
Yeah, sir.
Yes, sir.
Yes. All right. Any questions on what I've presented now?
No, sir.
All right. So you guys, I'm gonna be sending this, I think, late in the afternoon for you to go over, and also I'm gonna send the solutions for the other activities that I didn't send. I think it was exercise 8, which is this one here. I'm gonna be sending this. All right. Then I'm gonna send also activity exercise 9. All right. Yes.
Yes.
Then I'm gonna send, but consolidation, I'm not sure if many people have done. Let me just check people who joined us now. Who's this? Jolisha, Tandoeko, Oratili. Are you done with the consolidation activity?
Yes, sir, I sent it.
Okay.
Okay.
Yeah, Oratili, I think I saw that one. The others, Jolisha, are you done? Jolisha? Okay, Sakile, are you done? Bonello?
Sir, I think I'm almost done.
Almost done. Did you start or you still gonna start?
We're gonna start.
Still gonna start.
Yo.
Okay. The due date, I think I put it tomorrow. Ne?
Yes, sir.
Yeah. Okay. So you still have time. Please just try to do that, because I'm still gonna add more work, especially on this new topic that we are looking at. We are now doing physics, so we are done with chemistry. We are now moving on to physics. And for physics, I think till the end of term 2, it's just gonna be physics. So there's magnetism. Then we have magnetism. We have electrostatics. Then we have electricity, electric circuits. So please try to finish the chemistry so that we, when we do physics, we don't have to be going back to chemistry again. Right. So that's what we have. I'm not sure on this activity, exercise 9. Many people have got, I think, problems on what is this? Writing the chemical formulae. Are you fine here?
Yes.
Are you fine, guys?
Yes.
Okay.
Yes, sir.
Right. Last time, who's the Sakila? You wanted to ask something, then you got cut, I think.
So I don't remember.
Huh?
I don't remember, sir.
You don't remember? Okay. All right. I don't know if there are any questions. I think we'll continue in our next session. When is our next session?
Don't know, sir. Don't know.
Wednesday.
Wednesday. We skip one, then we do it on Wednesday. Is it fine?
Okay,
Yes,
sir.
Yeah. So in that particular lesson, I would look at revision of some of these exercises that I've been sending you guys. We'll look at the consolidation as well. Then we'll look at magnetism. Today it was a short lesson, so I didn't intend to extend the time, but maybe on Wednesday, when the time runs out, I'm gonna be having a code so that you join after the 40 minutes if maybe we don't have enough time. Is that fine?
Yes, sir.
yes, sir.
Or in terms of data, you guys, you still okay with that, no?
Yes,
Mm-hmm.
sir.
Okay. All right. So it's fine. Let's meet on Wednesday. I don't know if there is anything else that you want us to discuss.
No, sir.
No.
Okay, you guys maybe going back to school is gonna be maybe in when is this? June?
July.
July.
Huh?
July.
July.
July. That's what they say.
Yes.
Yes, sir.
June is for
Because
grade 12.
because okay, you're grade 10s. Oh, so it's gonna be grade 12 in June, 1st of June. Then grade 11s are gonna come maybe after 1 week or 2 weeks. Ne?
Yeah.
Yes.
Then you guys the
Yes.
other week. Okay, all right. So we'll see you in July. But I saw there they say they're gonna do away with the June exams. I don't know how far the school is gonna decide. Maybe you're still gonna write, maybe later on. I'm not sure.
No problem, sir.
Right, but at least the content we are covering it, so I think it won't be a lot of work. Then we'll take it from there. Okay, you guys enjoy the rest of the day. Then let's meet on Wednesday. Anything that you want us to discuss again on Wednesday? What I've said, is it fine with you?
Yeah.
Yes,
Okay.
sir.
All right. Okay, you guys enjoy your day. Then let's meet on Wednesday.
Yes.
Same to you, sir.
Okay.
Bye-bye.
All right. Bye.